Welcome to the 9th lecture for Physics 4C. As you have some time to take a breather and prepare for the optics timed assessments this week, in this set of lecture videos, I have put together some material that will help you take a stock of what you have learned in the last 4 weeks in geometric and physical optics. The first couple of videos are reviews of geometric and physical optics content we have covered, with some emphasis on the material that are particularly important for optics problem solving. While the timed assessments are not exactly the same as midterm exams referred to in these videos, also your assessments are open book, so you are not limited to a formula card. The overall review of topics you should feel comfortable with still applies. The second half of this lecture set are 3 examples of problem solving from the freeform timed assessment demos I have done in the past. In these demonstrations, I work out a 2-lens analysis problem, a telescope analysis problem, and a question involving a double-slit interference setup. Next week, we will finally start our coverage of modern physics, starting with special relativity.
Okay, so we don't have a lot of time, so let me use the remaining 20 minutes or so just telling you the topics that you should know for optics. And I'm going to try to do this from memory so that you can see that these are important topics. So the way I remember this is by first breaking down this one topic, optics, into basic categories. So there's 2 big categories and 1 smaller category that you should remember. The 2 big categories are essentially 2 different approaches to light. The geometric optics, that's what we spent a lot of time on. Sometimes this is also called, let me get different color. Sometimes this is called ray optics. And once you draw diagrams, then it makes sense because you're drawing a bunch of rays. And the other big set of topics is, I guess, let me call it physical. Physical optics. And the other name for that is wave optics. And this is where we had to deal a lot with the interference and the wave nature of light. So that's the basic breakdown in how we are approaching optics. So in terms of chapters, your chapter 1 was the introduction to all of this. It actually covered both of them. And chapter 2 was the, is that where we did the lenses? Yeah, so chapter 2 is the wrap up of the geometric optics. Chapters 3 and 4 are physical optics. Okay? So from those chapters, you can kind of see that it's going to be an even breakdown between them. 50%, 50%. Let me write that down. In terms of the importance in the topics, about 50% and 50%. Now, we did cover a little bit beyond this. On the first day, we actually started out with electromagnetic nature of light. And it's not technically in your textbook, or I guess you could call this Maxwell's equations. Oops, Maxwell's equations. And I wouldn't test you on Maxwell's equations because even though 4B is a prerequisite to this, but sometimes people forget 4B. But I do want to point this out, especially on the past exam, you will see quite a few multiple choice questions relating to this. And I'll probably scale it down a little, but it's still going to be some part of your exam. So I don't know, if I'm giving it a percentage, this will probably be somewhere between 5 to 10% of your exam, which means this had to get scaled down around, I don't know, 47 to 45 to 47% of the exam, 45 to 47% of the exam. So, I want you to keep this in mind. It's what's covered towards the end of Physics 4B and what I lectured on the first day. You had some. Did you have some homework questions on that? Not many. So that's why I'm trying to scale this down, because I didn't give you a lot of homework questions on it. So it'll only be to the extent, like speed of light. That's one thing that your homework question actually was relating to. So that's something you'd have to know. I think last semester I spent a lot of time on displacement current, and this semester I'm just gonna say I'm not gonna test you on that. Okay? So that's the main big breakdown. And what I want to do is list the smaller set of topics and formulas and stuff that you are supposed to know and understand within this. So with the electromagnetic nature of light, I think I can just write down one thing that you are supposed to know. Speed of light c is equal to 1 over square root of epsilon naught mu naught. Like, that is the one thing you need to know. That was in your textbook. And it relates to the fact that light is an electromagnetic wave. And what we lectured on was there's a whole derivation of where this comes from, and that will not, the derivation will not be on your exam. But you should know the result. Let me divide up the board so that I spend the remaining 15 minutes or so reasonably productively. Since I'm telling you they are about at equal level of importance, let me divide up the board equally into geometric optics and physical optics. And some things will be relevant to both of them. But I guess I'll just go in chronological order. If something mattered in covering geometric optics, then we'll start here, even though later on it'll be relevant to here also. So what do you remember from geometric optics? What do you remember covering?
Law of refraction and refraction.
Yeah, reflection and refraction. That's the very basic building block of geometric optics. In fact, everything else you do in geometric optics is the derivation from reflection and refraction. So you have reflection and refraction. So reflection says the angle of incidence is equal to angle of reflection. And your textbook covered how this came from Huygens' principle of the wavelet. Interesting reading, but it won't be really on your exam. The refraction is where you should remember Snell's law. So Snell's law says that index of refraction times sine of angle on one side is equal to index of refraction times sine of angle on the other side. And as you are remembering this is how I remember everything. Hopefully this reminds you. You have to define index of refraction. How is that related to other things? So I could have introduced this here, but now that it came up, let me just make sure we remember what index of refraction was. Index of refraction was defined as the refraction is equal to speed of light in vacuum divided by speed of light in matter. Okay? So if it's index of refraction of some material, then C is a constant, and speed of light in that matter would be property of the material. Okay? So this is the very basic starting point. But with the geometric optics, so the kind of problems you can do only with these will be limited, and they will actually be pretty difficult because they happen to involve a lot of geometry, and from my experience, most of people find the geometry difficult. Question?
So should the numerator and denominator reverse?
No, C is the greater number.
Yeah.
Greater number divided by smaller number bigger than 1.
I see.
That's how I remember things. Yeah. Good? Okay. So this is the basic relationship you should know. So let me just block this off. But most of the interesting questions you can do won't be limited to this. So when you think of geometric optics or ray optics, what's the, I don't know, the thing that you remember the most 2-3 weeks after when we have covered it? Like, you know, so this is the starting point, but there are some useful applications that we covered. Yeah, lens equation. So it's really, all of that would fall under what you might call, what color do I want? Let me call it optical devices. Optical devices. And over the expressions dealing with optical devices, the most important expression, number one expression, is the lens equation. 1/f is equal to 1/do plus 1/di. And coupled with this is a bit of ray tracing. So this algebraic equation is actually, it carries the same information as a geometric ray diagram does. So you should remember the ray tracing rules. And for, I guess, basic situation like this, with a lens of some focal length and some object here, you should know how to trace the rays to locate the image here. You should know how, so I guess the key phrase that you might, because you cannot search for a picture in your textbook, the key phrase you should know are the principal rays. So I drew two principal rays there. There's a third one that I almost never draw. So this is the most important thing when you are dealing with optical devices like lenses and mirror. And these, even though I prefer to draw lenses most of the time, this would apply equally well to curved mirrors. And so using this as a starting point, you should have some idea of a bunch of formulas that were derived. And you know, this is why you have formula sheet. That's where you would write down those formulas. Let me just name them. Some of them I probably do have it memorized, but let me just name them so that I won't be embarrassed by not remembering them. So some of the, let me call it list of formulas. So there's the image formation by refraction. So image formation by refraction. So that's when you have a single refracting surface that can form an image. So, you know, let's say air on one side, glass on the other side. And using this twice can actually give you the formula that we call lens maker's formula. Lens maker's formula. I don't think this really featured all the, I think this featured in your homework. I'm not sure if lens maker's formula was ever in your homework. Was it? Yes, maybe once or twice, not that much. So the number of times something occurs should tell you how important this is. Number of times this occurs tells you how important this is. These are sort of the kind of formulas that it's good to have in your formula sheet in case it comes up, but I wouldn't really hang on this being featuring heavily on the exam. And oh, maybe this was the more important one. Focal length of curved mirror. So this one I'm pretty sure I have memorized. The focal length is equal to a radius of curvature divided by 2, right? Yeah. So let's see, am I forgetting any formulas? I think that might be it. So these are some of the basic things to know in geometric optics. Then you go into the application of like, what do you do with this? So let me call it, I don't know, application. Applications. And once you start going into analyzing lenses, The way I would divide them up is kind of applications that involve single lens and applications that involve multiple lens. Right? So with a single lens, here were some things that you were asked to calculate or know how to handle. With a single lens, what would be the biggest thing? So this lets you find the, given two of these numbers, lets you find the third number. So given object and focal length, you can find the distance. What's one thing that you can calculate from that a question might ask that you might be interested in if you are actually working with the lens?
Magnification.
Yeah, magnification. So there's the formula for magnification. You have two different magnifications. Linear magnification, that's minus the I over dO. It's derived in the book. And there's also angular magnification, which becomes a little bit more tricky. So with the angular magnification, capital M, it kind of depends on the setup. If it's a simple magnifier, then the angular magnification was focal length, near point, divided by focal length for relaxed eye. And you can look up what it was for the strained eye. With the strained eye, it's actually +1 for strained eye. Good. So that's the single lens application. Wait, why did I say it's complicated? Yeah. So simple magnifier, so it's a single lens. If you want more than one lens, that's where you have to know how to handle multiple lens setup. Multiple lenses. And let me just, I guess I kind of didn't manage my space while I'm running out of space. Let me just tell you the things you should remember about the multiple lenses. So there's two examples of multiple lens setup that's worked out in your book. I don't ask a lot of questions about those either in your homework or anywhere, but I think reviewing those setup will help reinforce what you're supposed to know. So those two examples that are in the textbook are telescopes and microscopes. And really with the multiple lens, what you need to know is how to use, or let me put it this way, two lens setup, where you need to know how to use image from previous stage as object for next stage. It's conceptually simple, but as you might remember from some of the examples that we looked at, it's easy to make a mistake. So I remember an example in a lecture where we had a virtual image from the first lens, and many people thought that would become virtual object, but it was actually real object. And to wrap up this with, the thing that you should really be clear on with the geometric optics is this. You should be really clear on sign conventions, because this is really convention. So with the focal length, sign convention is simple. If it's converging positive, if it's diverging negative. But what the sign convention really highlights is your understanding of real and virtual images and real and virtual objects. So especially with the multiple lens, understanding what virtual object is becomes more important. So what sign convention is important for is real / virtual, distinguishing between those two for both image and object. Oops. Yeah. Good. So that's geometric optics. I think if you can do all the problem set questions, then you're probably fine. I wouldn't worry too much. So with the physical optics, let me try to list the things that you should review. You should review waves. It really starts from there. I wish it didn't have to, as in all of you feel comfortable with what you covered about waves in Physics 4a, that you don't need to review it, but that's really not the case. So you should start out with review of waves. And there are a few things to know about waves, like I guess you should know what all these symbols stands for. Wave frequency, wavelength, wave speed, knowledge that frequency is usually, knowledge that usually wave speed is property of the wave, and as the wave goes from one medium to another, frequency usually remains the same, all that stuff. Good. And this one relationship that relates these together, that wave speed is equal to frequency times wavelength. This one is one of those formulas actually that you can remember by dimensional analysis. Meters per second, meter 1/2. Okay? So you have that. Let's see, what else do you need to review about waves? Things like a superposition principle, and this relates back to the electromagnetic nature of light, that intensity is proportional to the electric field squared, because that features in a lot of the derivations you see. Yeah? And as you're reviewing about the waves, and this really matters for wave interference, the idea that you need to become familiar with is the idea of phase and the role that phase plays in interference. You've seen that, so the role that phase plays in two categories of interference in particular: constructive interference, and destructive interference. And for those of you who feel comfortable with this, to get constructive interference, you need integral cycles of phase, or integer multiple of 2 pi. For destructive interference, you need a half integer, or odd multiples of pi. Then the next challenge is to sort of how to take that and actually have an expression for intensity of something. And those specific examples are worked out as. So these are the basic underlying ideas. They are used to do some calculations that you saw in lecture and in the textbook. The kind of examples that you need to remember are the double-slit interference. Double-slit interference. And I guess actually the temptation for a lot of people would be to just jump right to this, because that's where you will have your first formulas, like d sine theta is equal to n lambda for constructive, d sine theta is equal to n plus 1/2 lambda for destructive. Like that's where you find the formulas. But I'm really telling you that before you get into the formulas, you need to be on a solid ground with understanding of the interference. Because if you start from here, as you go into the other example you will see is a single slit interference. Single slit diffraction, which is a result of interference. You are going to get confused, because with a single slit diffraction, the destructive interference actually kind of looks like this. And it would not be that confusing if you remember the basics, because the basic thing that we apply with the phase doesn't change no matter what the application is. So these are the two biggest applications. The other applications that you should know, and I need to assign the homework problems on, are the thin film interference, interference. And I thought there was at least one more. What am I forgetting? Oh, and slit interference, which really lead to diffraction grading. I think that might be it. Did I forget anything? Anything big? Yeah, so double-slit interference, that's chapter 3. So this is, as you are reviewing, so this is the place where you should make sure that all these things you are supposed to review and know, that it's on solid ground here. Because the kind of calculations and geometry considerations you go through here in chapter 3 is the knowledge and familiarity you will use for analysis of single-slit diffraction. I think this is still chapter 3, but see, I feel like I've forgotten something. Well, let's see. I'm out of time, but let's see if I've forgotten anything. So that was the promise, and now I have all this laid out. Let's see if I've skipped any of the sections. We did refraction. Okay, so there are these things that I did skip. Total internal reflection, polarization. So, these are smaller topics. Which is why they didn't fit here. So total internal reflection, that surprisingly actually goes with the refraction, if you remember the critical angle, right? Yes. Polarization, so that's the topic of today's lab, and it'll be a small portion of the exam. I guess if I need to fit it somewhere, polarization would really fit in with it here, polarization. Because the moment you start talking about polarization is when you have to explicitly refer to the electric field. You have to know that not only is light wave, it is a wave of electric field. That's where polarization makes sense. So we are covering this in today's lab, so it's a kind of, that itself is an indication that it's kind of a small thing. Let's see, Huygens, so okay, week 2, we did the images. So I guess maybe I probably should have written down explicitly images and whatever, but I think it's kind of all implied here. So, so image formed by refraction, lens equation. Oh, I forgot the eye. So, well, I would qualify as single. It can actually fit in both places. It could be, depending on the setup, it could be a single lens application, lens of the eye, or it could be part of a multiple lens system. Like if you have a corrective lens in front of it or something. So yeah, magnifier, microscopes and telescopes. Week 3, that start with the double-slit interference. And so this is where things can get more mathematical. This is where we are doing all this complex exponential stuff. And I just say it's good for you to know. Someone like an A student would have worked through this problem set and would have done well in the end. But as you're preparing, so that's sort of later in the list. It's I would actually make sure that I remember, I'm familiar with the single-slit diffraction. And what your textbook is calling double-slit diffraction, this is what you saw in the lab last week as sort of superimposed pattern of both the single-slit diffraction and double-slit interference. So that's all encompassed here, double-slit interference and single-slit diffraction. And what we covered, what we finished covering last Tuesday are all these: interference in thin film, multiple slit interference, which leads to diffraction grading. And I can't believe I forgot this. So I mean, all of this is leading to something important. And sorry, I got distracted by running out of time. This is important for an experimentalist, and it's conceptually important as a recurring theme in this class. It's diffraction-limited resolution. And it's what it's in your textbook as circular aperture and resolution. Or if you are looking for a single thing for you to remember, then it would be the Rayleigh criterion. I can almost guarantee that if there aren't those questions in the past semester's exam, that's one of the things I mean to fix. And the theme, since you will start, I'm hoping you will start to notice it as we go throughout the semester. The theme of this semester is actually this: limited. So far in physics, you haven't really been told about things that are not possible, right? Maybe the one thing we told you is energy conservation. So it is impossible to create energy or destroy energy. And that was kind of it. And the sort of biggest theme in modern physics is development of theories that actually tells you things that you might have naively thought as a child should be possible. Like you can have infinitely, arbitrarily precise microscope. This diffraction-limited resolution tells you that is not actually possible. There's and this limited, it will be a feature of that. You will see that in special relativity, universal speed limit, and you will see that in quantum mechanics.
So let me do that one attempt for the test student and see what that looks like. I don't know what test student is gonna get. I think this is the question I've nicknamed two-lens analysis. And I remember this as being a particularly long question, so I'll be quick about doing this. Okay, consider an arrangement of a converging lens, okay, of some focal length f1. Who's gonna say this is f1? And a diverging lens of focal length and d is greater than, yeah. So let me draw the diverging lens. I do recommend drawing figures as a matter of just good problem solving practice and making sure you understand what the question is asking about and all that. Okay, yeah, this convergent lens is stronger than the, I didn't draw it to scale, but I will note that f1 is less than f2. Two lenses substantial distance, yeah, so this is my distance d. Perhaps arrange so that the convergent length is the location up. So this is my x is equal to 0. Diverging length, yeah, so this is my plus x direction. Okay, yeah, and the one limitation of this system is you can only enter text answers here. That's one of the reasons there's an add work feature at the end, so that I can have people add the diagrams and all that. So, so part A says consider an object placed at the location. Okay, I'm just gonna draw it here, but kind of far enough away. But this is supposed to be 3f1, or x is equal to minus 3f1, so that the light from the object will first go through the converging lens and then the diverging lens. Let me do a brief ray diagram just so that I have some intuitive sense of what's going to happen. So I'll form a real image somewhere here, maybe. It's possibly inside the focal length of the diverging lens, if in case that's relevant. So this will now form a image through this, and if I continue to do the ray tracing, so okay, so this will be where the virtual image due to this diverging lens forms. So that's the ray tracing, just to me trying to make sure that I understand the setup. Find the location of the image being formed by the converging lens. And okay, so I need to answer this part, the stuff relating to this image here. So for actually getting an answer, I won't use the diagram. Again, it's not to scale. But what I can do and should do is I should use the lens equation. I have the thin lens equation, which tells me the relationship between the object distance and the image distance and the focal length. And I think I'm given the object distance. So when they tell me this is the position of the object, that's not the object distance. That is, so I need to work out, is this a real object? Yes. So my DO is positive. So my DO is 3F1. Image distance, I need to work it out. I know, well, F1, I'm treating that it's given. So with that, I'm going to do a little bit of algebra. So solve this for DI. I'm just going to do that in my head, which comes down to me just recalling a formula that I have written down so many times that I have it memorized. But you can, in the interest of time, I'm just going to, do that in my head and then plug in the values. So DO is 3F1, so I have 3F1 squared. On the denominator, I'm factoring out F1, I have 3 minus 1, so 2, I have 2F1. Okay, so my image distance is positive, 3/2 F1. Okay, find the location of, okay, so the location of the image will be X is equal to 3/2 times F1. I think that's it. And and all this is manually graded, so if whether you enter it as F1 or F_1 doesn't really matter. I think I got into habit of not putting subscripts because when you're programming, this is a much easier variable to work with. And then C attach the work for diagram, lens equation, etc. So the purpose of this really is for me to be able to separate, what was worked out within the time limit. So I do recommend that after the time limit, you do kind of organize. You are allowed to change this, organize it, make it so that you have a better confidence that I will be able to understand it. So part B, okay, same set of find where the final image through the diverging lens appears to be and give the, okay. So so for this analysis, I'm treating this as my object and for this second lens and then working this through. So the lens equation remains the same. What I need to be careful is working out the object distance. So 1 over DO plus 1 over DI is equal to 1 over minus F2. And the object distance should be this distance here. That's the object distance. So this image distance from above, that's telling me this distance here. So this is one of the purposes for the diagram. I can kind of see from the diagram that this DI plus this DO should be equal to this total distance between the lenses. So I'm gonna go write that down. So the so total distance between the lenses is the DI that I worked out, 3/2 F1 plus the DO2, so that I don't confuse my stuff. Yeah, and it looks like so. So I need to solve this for DO2. My DO2 will be total distance minus 3/2 F1. So this is all in terms of known quantities. So I'm going to treat this as known and do the rest of the work for DI2 in terms of all these other known quantities. And doing the algebra in my head, which again, as I admitted, is me just recalling the formula I've written down so many times that I have it memorized. But let me write it down anyway. DO2 minus F2. All right, there's some simplifications. These cancel out. So yeah, I'm gonna get an overall negative answer, which is what I was expecting because the diverging lens is gonna form a virtual image. So it would be minus DO2 times F2 over DO2 plus F2. And at this point, I guess you do have some choice. You can choose to plug this into your expression so that you can put in an answer all in terms of the known quantities. That's possible, doable. What I would recommend instead, or not instead, what I would say is acceptable as well, is as long as you are defining your variables, you can write your answer in terms of that defined variable. So you could say define DO2 is equal to D minus 3 half. This basically saves on some writing. You are perfectly allowed to do that. Now, if you have said X is equal to minus DO2 times F2 over DO2 plus F2, that would be wrong partly, not because the answer, the work here is wrong, or not because you're using DO2, not because of that, but because you're putting in the image distance for what should be the X position. So I need to go back up and figure out okay, given this image distance, what is my X position? So, my X position, whatever this is gonna be, it should be the distance minus the absolute value of the image distance. So what this should be is, so that's the image distance. So the X position should be D plus the image distance with the negative sign included. So that would be correct. So yeah, you can enter it that way, and same deal. C attached will work for diagram, lens equation, etc. Again, my goal is to separate out what was done within the time limit, and in terms of the organizing work, you are allowed to do it after the time limit. And that's partly the reason, the way I justify such a tight time limit of 20 minutes. You can see even me, while I'm explaining, I have to do the rest without explaining because I only have 9 minutes. Okay, what is the linear magnification of this arrangement? Yeah. So I'm kind of recalling the magnification formulas. For each stage of this, the linear magnification is minus di over do. That's the formula you should be using. And so this is for the entire arrangement. So you have to do it in 2 steps. So the overall magnification and total should be basically magnification of the first stage times the magnification of the second stage. So magnification of the first stage is, I think I have those in terms of, di is that. So minus 3 halves, 3 halves f1 divided by, I think I remember the object distance, 3 f1. And okay, 3 is cancelled. Okay, so the first stage had the magnification of 1/2, so it shrunk rather than magnifying. And the second stage has that image distance, and I don't know how much it'll simplify. Let me just first write it out and say DO2 times F2 over DO2 plus F2. That's the image distance times 1 over the object distance. I can just write out DO2 because I think it's going to cancel. DO2, yeah, it'll cancel that, and minus F2 over DO2 plus F2. And I think I'm going to leave the final answer in terms of this. So the overall magnification should be product of this, M1 times M2 minus signs. Wait, there's the minus sign, so this minus sign should have canceled that. So it's overall negative magnification. I think, and I'll just be safe and include it. So this is the magnification of first stage times the magnification of second stage, F2 over U2 plus F2. So yeah, let me just write that out. The total magnification is equal to minus F1 divided by 2 times F2 divided by DO2 plus F2. And I guess if you're answering this way, you would be doing me a favor if you basically, so it says in terms of given quantities these, and I am using DO2, so I should define DO2 in terms of the given quantities, which was here. So I say DO2 is D minus 3 over 2 times F1. So with this, all this is in terms of the given quantities. And all this is doing is it's saving you some writing work here, and all that is a lot. What I would ask for is please define any variables that you are using that I haven't already spelled out as known quantities. So, all right. Consider your work in parts A and B, where you find the location of the first image and describe and explain what you see. It goes to whether I'm forming a real image or virtual image. So, okay. And here I don't think I need to do any work here because it's a conceptual thing. I more or less want to see this. So I have to say, okay, I have to say, so for one, the converging lens forms a real image. So a screen placed at the location of image 1 will show the sharply focused image. Part 2. This image serving as an object for this lens, it is a real object. I think watch the lecture on sign conventions. But the image it's forming, it's a virtual image in that at this location, no real light rays actually crossed. This light ray appears to come from here, but it doesn't actually cross there. This light ray does come from here, but it's not forming a sharp focus with other light rays here, like not literally. So it's a virtual image. So what I would say is that the screen placed at the location of image 2 does not show a sharply focused image because the diverging lens forms a virtual image in this arrangement. There are other arrangements where you can form a real image with a diverging lens, but not this setup. So you are welcome to submit an end. You are welcome to add work here. What I will warn you is that when this time runs out, it'll kick you out, and you may lose the work you've been typing. So I would almost rather just submit an end and keep working on the work later. And so the system will timestamp your work, but again, there's no time limit for the work. This, to me, the best, greatest utility for me is so if someone somehow changes their work after I've graded it, then it lets me know. Because as long as it's before I grade it, you can change your work all you want. It doesn't matter to me. Yeah, okay, I think that's it for this question. So let's start. All right, that's a new question. So let's do that. Okay, you are trying to build a telescope. Okay, I see that. Okay, 2 converging lenses. Enter text answer. These numbers might not be randomized. I should have randomized it. Describe the arrangement. So let me just draw the picture because I think I remember from, I remember it from somewhere. You might remember it from lab. So if you have an optical axis, and let's imagine you have your objective lens here of some long focal length, like 150 centimeter. Then the way you would have to set up is so that the focal point of the both lenses are overlapping. So with another converging lens as the eyepiece, the eyepiece would need to be somewhere here with its focal point at 15 centimeters away, kind of overlapping. That's how you need to set up. That way, if you got some sort of you got parallel light kind of object from far away, it'll focus here at the focal point of objective, and the eyepiece will be at just the right place to form a virtual image at an infinity distance away. Something like that. Okay, close enough. So with that drawing in mind, I'm going to describe it here. So the two lenses should be separated by 165 centimeters so that the focal points of the two lenses are overlapping. Let's see. Extend the work, include the diagram. Okay, I think, and I can explain so that the final virtual image of a faraway object will be formed far away, meaning it can be seen, it can be focused with relaxed eyes. So that's A. B. The setup above is for relaxed eyes. You decide to see if you can get a greater magnification if you decide to strain your eyes a little. First, you start adjusting L. Okay, you change the distance. So I think now you're going to be given a distance. So let's do that. So for part B, we have the same two lens setup, but now what's different is instead of figuring out what their distance should be, now you've been told that the distance between them is 159 centimeters. L is equal to 159.4 centimeters. So it's shorter. Before it was a total of 165. Now it's 159.4. Okay, and what is it? Find the location of the final image relative to the eyepiece lens. Also described image. Okay, good. So so this is what you work through. So you analyze each lens one at a time. So here's a lens with 50 centimeter focal length, and you have some object DO that's approaching infinity. So you go through the analysis to see where the image will be. It'll be at the focal point, but let me just go through the analysis. So you use the thin lens equation, 1 over DO plus 1 over DI is equal to 1 over F1, or F objective. Then with the DO going to infinity, this whole thing goes to 0, which means 1 over DI goes to F object. So DI, image forms, a real image forms at the focal point. That's what we talked about up there, and that part doesn't change. The only thing that changes is how far away is the eyepiece. So now I'm gonna do the second step of the analysis. So having found the image here, that becomes now the object for the second step of the analysis. This is gonna be DO prime. It'll form some image somewhere. I think it's gonna be somewhere out there. Virtual image. So let's write down the equations and see. Let me get rid of these so I don't have to, or actually never mind. I think I can scroll. It's not too much scrolling. So let's work out the second stage. So second stage, we are saying 1 over DO prime, whose number will work out from the numbers given, plus 1 over DI is equal to 1 over the focal length of the eyepiece. So solving this for DI should be 1 over focal length of the eyepiece minus 1 over DO prime. So I should figure out DO prime. So from the numbers given, DO prime is 9.4 centimeter. Okay, I think I have enough. The rest of the calculation I can do in Wolfram alpha. That's the quickest way to do it with a limited amount of time. 1 over the 15 centimeters, that was the focal length of the eyepiece, minus 1 over 9.4 centimeter, that was the object distance. Yeah, I think I'm gonna get a negative number. Let's see, minus 25. Oh, yeah, I could have guessed that, I guess, because this is a like textbook near point, 25 centimeters. So my answer, which I could have guessed if I thought through it a little bit better, is a minus 25.2 centimeter. But I think in any case, even if you could have guessed it, you should still like derive it anyway, so it's fine. So final image is 25.22 centimeter away from the eyepiece, on the opposite side from the outgoing light waves. Virtual image. So it's virtual, and I think it's going to be it'll be an inverted image. And if you want to justify why it would be inverted, you would be working through the total magnification, which is going to be equal to magnification of the objective times the magnification of the eyepiece. And when you work out magnification of objective, which is equal to minus di over do, that's going to be negative because both the do and di are positive. So you start out with a minus inverted image here. And when you do the eyepiece, because your object distance is positive, image distance is negative, the magnification will be positive. So minus times plus, your total magnification is minus, meaning inverted image. So that's B. What is the total angular magnification of your setup in B above? So you gotta work through that. Do I have enough time? Got 10 minutes at least? Okay. So I think the easiest thing to do is figure out the angular size of the thing. So, it says you may assume that you are looking at that. Okay. So, let's follow the hint. It says start with the definition of angular magnification, which is going to be the theta of the final image divided by theta reference. And here, because it's a telescope, theta reference will be basically given by 2 meters tall divided by the distance 1 kilometer away. That kind of gives you the angular size of things at small angles. I don't have to bother with the arcsine, arctangent when it's a small angle. So for theta image, that's where now I should work through. So I already worked out the image distance. If I work out the final image height, then I can do the, for the theta image, I can do the image height, height of the image divided by this image distance di. That'll give me the image angular size. So let me actually copy and paste this expression that I was writing. Because so to figure out the image height, you need a linear magnification. So let's start there. Your linear magnification was that. So I think I need to figure out and it kind of helps me that the question is letting me use some actual distance of the object, because otherwise I think my the linear magnification expression for objective lens minus di over do, if do is infinity, di is it's like you get something that's a zero. I don't want to deal with the zeros. So it's gonna be minus, I think I can keep the di as being basically the focal length of objective. And do, instead of being infinity, it'll be 1 kilometer. So I can get some numerical value for magnification of objective lens. And then magnification of the eyepiece will be minus di prime over do prime. And I think I had a do prime number. So this, let me just type in the, put in the numbers from above. Image distance was 25.2 centimeter. Object distance was 9.4 centimeter. 9.4 centimeter. And let me forget the minus signs. I'm just dealing with the absolute numbers. So let me work out the number above there. That's gonna be objective 150 centimeter divided by 1 kilometer. That'll give me some number 0.0015, and let me do that times this ratio. That will give me total magnification times 25.2 centimeter divided by 9.4 centimeter. So with that total being equal to 0.00402, I can get the height of the final image as m total times the height of the object. So I already have m total there. I just need to multiply the height of the object 2 meters. So that times 2 meters. And it's going to be smaller than 2 meters, I think. It'll be, 0.804 centimeter. That doesn't mean it has a less than 1 angular magnification, because we have to go through this final calculation. So, so let me use height of the image of 0.804 centimeter. And the image distance, this is the part that gives you the angular magnification. Image distance is 25.2 centimeters. So the theta image will be, I guess I can actually use this number. All of this divided by 25.2 centimeters. So that's the angular size of the image. So take that, divided by the reference angular size. So take all of this, divided by 2 meters divided by 1 kilometer. That'll give you the angular magnification. And you get 16. Okay, so I'm gonna put in 16. So m is equal to 16. Is that good or bad? I can't tell. Let's see, 60 minutes. So in the ideal setup, your angular magnification must have been 10, the ratio of the two focal lengths. So from 10 to 16, I think that is better. Work attached. And for the work, I'll attach this and this page, because I think that basically contains all the numbers that I'm putting in. So and in this number, you can kind of see how 1 kilometer would have canceled out. So if an object is actually infinite away, that's actually fine. It'll have canceled out. It's just that earlier when you're plugging numbers, that's in the way. So with the strand, I guess angular magnification is better. Good. As you look at a friend 1 kilometer away, you ponder the question, what is the smallest thing you can see? So the additional information you need is the main information I need is the aperture size of the telescope in order to apply the Rayleigh criterion, which is, I always forget this. So theta mean is equal to 1.22 times wavelength divided by aperture. I think that's correct. I forget where 1.22 goes. Oddly enough, I remember the number itself. For the wavelength itself, we can reasonably assume it's around 500 nanometer for visible light. All right, I think I don't think I'm being asked the actual angular resolution limit. So that's my answer. I guess I'm done. So I got 4 minutes, but I think I did everything. I think there's a version of this question where it's not a converging lens, but diverging lens. That'll have its own consideration. One thing that I can say is still the same is the description I gave earlier, how for A, you overlap the focal lengths. The way with the diverging lens it overlaps would change to where the lens is here. But for this diverging lens, you consider, you have focal point there. So that's what's overlapping. So that part, the description that the focal points are overlapping, that still remains the same when you do the diverging lens. Just have to be careful on which side you place it. So, okay, I think that's everything. Let me just attach work and submit. Right, so that's everything. Let me submit it. Go in with the instructor access to double check that I got the correct. I want to mainly double check that this answer 16 is right. Because there's a chance I made a mistake somewhere. I don't know. Submit and I did put a lot of care into coding in the answer keys, so what's in the answer key should be right. So this is the test student work being viewed under instructor access. Let's see here. Did it ask for? Oh, it did ask for angular magnification. I forgot to give it. Oh, oops. Yeah, you should give it. I did say it out loud that it's gonna be 10. Yeah. All right. Setup is for relaxed eyes. Final. Yeah. Yeah. Is 25.18 or 2. Yeah. Good. And here, let's hope 16. Okay, good. Correct. Yeah. Yeah, at least with I think if you get the diverging lens version, this is I found that it's less with the diverging lens. Yeah, I wouldn't have guessed it. I would have guessed that with both types, somehow if it's a strained, you'd get bigger image, but with the diverging lens, you get smaller magnification. And here, yeah, I think that's basically it. Yeah. Good. So I don't think I made any mistakes here. So that's this question. So let me start on this. Again, I don't know what question test the student will get. Okay, that seems reasonable, I think. Yeah, okay. This is one of those. So, where these questions come from? They come from my past midterm exams, and some of the questions are, I don't know if they're the best questions for this kind of format where the answers you put in here are a bit limited, and a lot of what you attach is what you have access to after time limit. So yeah, is show that outgoing angles for which line expand. So and I think here I give you the answer basically so that if people put it in something like this, I can say, I mean, even if you organize it a little bit, I can say, well, that was in the question. So, can you demonstrate to me that you can contribute something that wasn't already provided in the question? And this is the kind of question where it's basically asking you to reproduce the steps that are that you see in the textbook. But so it is open book exam, which means you are allowed to look at your textbook. All that is built into the expectation. You are allowed to look at the textbook, and this is really one of the reasons for the time limit, because if you spend a lot of time reading through your textbook while you are trying to do this assessment, then you'll run out of time. Now, having said that, okay, so I think it's basically the derivations here. Wait, does your textbook not do the derivation for this thing? Maybe not. So, so for this particular question, I guess there's nothing you can actually just copy and paste. So this figure actually includes a lot of the arguments you would be making. Oh yeah. So you are allowed to see all this while you're in the assessment. Again, that's what open book means. But even on open book assessments, the answers you turn in, the work you turn in has to be your own work, which means if you do something like this, as I'm grading it, I'll look at it and say, hey, that's basically the textbook. Could you please submit your own work? Probably won't go as far as saying that's cheating, because once academic dishonesty gets involved, it's a whole thing that I would rather not deal with. But you also won't get too much credit for basically copying what's in the textbook, because I know you have access to the textbook. I want to see your reasoning process. I want to see explanations in your own words. So model answer for this part A would be something like, okay, constructively interferes are given by that. So thinking back to the lecture that I have watched, again, I've also given for me, but imagining the test student who have seen the lectures, the test student will remember, okay, constructive interference means the phase difference, delta V is equal to some integer multiple of 2 pi. So, whole cycles difference. The phase difference comes from the path length difference. Looking at the geometry, that would be this geometry here. I might draw some figures here that's in the textbook. The path length difference there is delta x, path length difference, is equal to the hypotenuse. Let me draw some of these figures so that I'm not just gesturing with a mouse. So it's this geometry I'm thinking of. Drop down a perpendicular line. It's this right triangle that gives you the geometry stuff to figure out this delta x here. So the delta x is equal to hypotenuse times sine of, and you need to work out that this is a theta as well, sine of theta. The path length difference leads to phase difference in this way. Delta phi is equal to the path length, and let me just clear the annotation. The path length difference in units of wavelength, lambda, but that's the kind of phase difference in cycles. I need it in units of radians, so times 2 pi, that's the phase difference. So we say, okay, this whole expression here is equal to the condition that I set outside before for the constructive interference. I did a copy. So kind of looking at these expressions here, 2 pi's cancel. I have, so I get something like, wait, delta x, that's not right, sorry. Oh, yeah, sorry, I copied over the wrong thing. This is what I should have copied over. So this is the, okay. Yeah. So where I have delta x, this should have been it, because d sine theta, that is delta x. Okay, so let me have that, and okay, 2 pi's cancel, so I have d sine theta over lambda on the left hand side, move the lambda over to the right hand side, so I have d sine theta is equal to n times lambda. 2 pi's canceled out. Use m for better convention. So how much of the detail? So here, this is a bit of an over inclusion. Typing all this out takes time. You can kind of say I'm already kind of behind in time. So if you are instead writing this out mostly on paper, and you just want to sketch out, like maybe write down the equations line by line without having a narrative explanation, that's fine. Really, the biggest kind of the separation role of answers versus work is that answer tells me what you figured out within the time limit. So give me enough of the breadcrumbs to connect the dots. And in your attached work, you can expand this a lot more. So here I might say, okay, same reasoning as above, except that phase difference relationship is delta v is equal to n times v, where n is up. and you can work through the rest. And in going through the rest, you might have in order to say that n is odd, you might have n is equal to 2 times m plus 1, where m is any integer. This ensures that the integer n is odd. And in fact, going through the rest, you with this you can like this is, but it ends up being when you do that. Now here I might actually write up a little more to kind of show a couple more equations that lead to this. In the attached work is where you would fully fill it out. Derive an expression for the intensity of the interference pattern on the projection screen as a function of outgoing angle. Yeah. So this it's basically asking you to, so you should review your work before review lectures, study before you start, and these parts of the questions, they are basically asking you to reproduce some of the derivations that are done here. And I think the easiest version of the derivation to reproduce is the one where I use complex exponentials. So I have analysis of double-slit interference with the complex exponentials. There is there's a 20-minute lecture that does that. I don't have 20 minutes now to reproduce this. I'm not going to do that. And you also won't really have time within the assessment to watch through this within the 20 minutes total of the thing to do that. But the idea is that if you've watched and all the things I'm doing here made sense, then you had the time to kind of absorb all this and to reproduce this on the assessment. You should be able to do that in 5 minutes. So, and because you're limited to typing, just type out enough portions of something that comes from this to demonstrate that you understood the attached, demonstrate that you understood, and two, that you typed it in during the time limit. So that's for that. And this is also, oh wait, this is conceptual. So, I can say this, intensity minima won't be completely dark because the cancellation won't be 100%. I'll leave that there. Okay, submit and end. Oh, by the way, don't do what I'm doing now, which is I'm just leaving this blank now. Anything that you leave blank, that will severely limit how much credit I can give you. Because basically, if this is blank, I don't have anything to anchor what you are turning in your work as. So you should put in something so that as I'm grading it and as I look at your work, I can kind of try to figure out which part of the work is associated with the answer you submitted within the time limit. And if you somehow made substantial modifications to the work, which again, I'm not prohibiting, because it's hard to say both encourage you to organize your work while prohibiting addition of more material. So, but if you leave it blank, I basically have to assume that everything in the attached work was done after the time limit, which limits how much credit I can give you. Depending on the quality of work I see, I might not be giving 0, but it makes my job a lot, makes the decision process for me a lot easier if I see something here so that I can try to figure out which part of the work is from within the time limit.